Welcome back to Very Ordinary Differential Equations. In this lecture, we discuss using power series to solve higher order equations. So let's suppose we have a differential equation in our standard form. This is now a linear, nth order differential equation, possibly non-homogeneous. We're going to assume that all of the coefficients are polynomials, that p naught of x naught is not zero, that f of x can be written as a power series centered at this same x naught with a positive radius of convergence. Under these assumptions, all of our existing experience with power series solutions will work just fine. Because p naught of x naught is not zero, we are at an ordinary point. If f of x can also be written as a power series with a positive radius of convergence centered at this point, then both sides will have a positive radius of convergence centered at that point. We're also assuming all of the pi of x are polynomials because it greatly simplifies our lives trying to multiply power series by polynomials rather than multiplying a power series by a different function. Examples of using techniques in power series to solve higher order equations can be pretty long, however. So we're actually only going to work through one example rather than the typical three. So here's the one example we're going to do. Solve the initial value problem, x squared plus 2 times the third derivative of y minus 3xy double prime plus xy prime minus y equals e to the x, where y of 0 is 1, y prime of 0 is 2, and y double prime of 0 is 2. Now the coefficient of y triple prime is not 0 at x equals 0. In other words, 0 is an ordinary point. Also, our forcing function e to the x has a very well-known power series representation centered at 0. So we're going to go ahead and assume that y is written as a power series centered at 0, and here is our standard power series for e to the x centered at 0. As we've done previously, we're going to go term by term through the differential equation, computing each of these as in terms of power series, performing all the same tricks of re-indexing and power matching and all of that. Okay, then what we're going to do is say, once we have a single power series on the left equals a power series on the right, if two power series both converge to each other on a positive radius of convergence, then all of their coefficients must be equal. So here's the power series for y. If I take a single derivative, okay, don't forget that the constant term will vanish when I take a derivative, but if I multiply by x, this power goes back up by 1. So we'll end up with the sum as I goes from 1 to infinity of I, a to the I, x to the I, but I equals 0 can be reincorporated into that sum with no problem because that term, I equals 0, will just give me a 0. It does not change the value. So here's a power series starting at index 0. The power of x matches the index for the term xy prime, there. If I was then going to subtract y, xy prime minus y, since we know in our differential equation we eventually want to do that, well, I have this power series, I ai x to the I minus a single ai x to the I. Altogether, this gives me I minus 1 ai x to the I. So here was our power series for y prime. Notice the index starts at 1. If I take another derivative, we'll end up with I minus 1, aix to the I minus 2, starting at index 2. Here in our differential equation, we need 3x times that. So we're going to multiply by negative 3x. The negative 3 comes in, no problem. The power of x goes up by 1. So now our series starts at index 2, and the power of x is I minus 1. So the first order of business is to re-index this so that the power of x matches the index. At the starting index of 2, we have a power of 1. So we're going to start the series at 1 and call that our power of x. Since we had to increase this index by 1, we have to increase all of the others as well. Now we have a series starting at 1. We would really like the series to start at 0 so that it matches all of the others. So we ask, what happens in this series for the term corresponding to I equals 0, the missing term? Well, if I equals 0, the whole term vanishes. So I can add that term back into the sum at no cost. So I can start this series at 0, because all we've done is add in the term for I equals 0, which amounts to adding in 0 anyway. So now I have a series going from 0 to infinity where the power of x matches the index. So now I have a power series that will be convenient to work with for the term minus 3xy double prime. Here was our general series for y double prime. We're going to need to take another derivative. So by default, if I just take another derivative, the term corresponding to I equals 2 is the constant term here, so its derivative vanishes. So now I have a series starting at index 3. I minus 1, I minus 2, ai x to the I minus 3. I've taken 3 derivatives of my general power series. Now on the one hand, in our power series, we're going to need 2 times this. So we're going to go ahead and figure out what that looks like right now. Well, we end up with a 2, and we simply have to re-index this series so that the power of x matches the index I. Notice that when I is 3, the power of x is 0. So I can go ahead and start this at index 0 right away. That involves raising this index in the exponent by 3, so I have to raise it by 3 everywhere else. So I get ai plus 3. I minus 2 becomes I plus 1. I minus 1 becomes I plus 2. I becomes I plus 3, and we were multiplying by 2 anyway. So here is a nice convenient power series for 2y triple prime. But we also need a power series for x squared y triple prime. So going back to here, the totally unmodified power series for y triple prime starting at index 3, note, if I multiply by x squared, the only effect is to raise the power of x by 2. Now what we would do is we would re-index this. At I equals 3, I end up with x squared. So this should now start at index 2. However, the form you would get would be I plus 1, I minus 1, ai plus 1, x to the I. The missing terms of I equals 1 and I equals 0, well, when I equals 1, you'll get a factor of 0. When I equals 0, you get a factor of 0. So both of those terms can be freely reincorporated into the series. So now we have a convenient power series. When I say convenient, I mean starting at index 0, and the power of x matches the index I. Now we have a convenient power series for x squared y triple prime as well. Therefore, I can add these two power series together to get a nice power series for x squared plus 2 y triple prime. We've got various coefficients times ai plus 1, but we also have various coefficients ai plus 3. Once I distribute out all of these polynomials of I and collect terms, it's a little simpler to write it like this. Okay, so we have a third degree polynomial, ai plus 1, and another third degree polynomial, ai plus 3. And this is just the power series for this first term here, x squared plus 2 y triple prime. So now what we should do is we should take the power series we just generated for that term and subtract this power series here. So here's the power series for x squared plus 2 y triple prime. Here is the power series for minus 3x y double prime. So they match index 0 to infinity. They match x to the I. So we just have to ask, what's the coefficient of x to the I? Well, we have a whole bunch now of ai plus 1s. Okay, notice that the coefficient with ai plus 3 did not change between the two expressions because the only thing we've introduced here is more stuff times ai plus 1. So we take I cubed minus I, ai plus 1. We're going to subtract 3i squared and also subtract 3i. So altogether, it's I cubed minus 3i squared minus 4i times ai plus 1, and then the same terms of ai plus 3. So now we have a nice power series for these terms of the differential equation. Having just determined a power series for these terms of the differential equation, and having earlier determined a single power series for these two, we can now just combine them. So here's the power series from the previous slide, all of this times x to the I. And several slides back, here was the power series for xy prime minus y. Notice that they both have x to the I. They both go from 0 to infinity in their index. So we can just look at the coefficients of x to the I. I've got a bunch of stuff times ai plus 1, a bunch of stuff times ai plus 3, and a little bit of stuff times ai. So there it is. These two bits haven't changed at all. We've simply introduced I minus 1 times ai. So now we have a power series for the entire left-hand side. But that entire left-hand side is equal to e to the x. So the power series for the left-hand side must be equal to the power series for e to the x. And since we now have two power series equal to each other on a positive radius of convergence, we conclude that all of the coefficients must be equal. So the coefficient for the power series on the left must be just 1 over I factorial. So here is our recursive relationship for the coefficients of our power series solution. We're going to solve this for ai plus 3. It's not terribly hard. I'm not even going to do any simplification. I'm simply subtracting all of this, then I'm subtracting all of that, and then I'm dividing by 2i cubed plus 12i squared plus 22i plus 12. So if you know the value of ai and ai plus 1, you can now determine the value of ai plus 3. So the initial conditions now come into play. Here was our power series solution for y as a function of x. Y of 0 must be the initial term a naught. We were given that y of 0 is 1, therefore a naught is 1. Y prime of 0 is a1. Since we were given y prime of 0 is 2, we conclude that a1 is 2. Y double prime of 0 is not a2, however, it's 2a2. The term in this power series would have been a2x squared. So when I take two derivatives of x squared, I don't just get 1, I get 2. So we would end up with 2a2 here. So y double prime of 0 is 2a2. Since we were given that y double prime of 0 is 2, we conclude that a2 is actually equal to 1. So now what do we have? We have a recursive relationship for the coefficients, which involves ai plus 3 in terms of previous terms. So it's a 3-step recursion, but we also have 3 initial terms of the sequence. A naught is 1, a1 is 2, and a2 is 1. So here's our recursive relationship and our first 3 terms. This really does define the entire solution at this point. It's not in any way easy to recognize this as some sort of standard function. Okay, but it's a power series solution. Power series solutions are not pretty usually. The point is that you get this recursive relationship, you have some initial terms, which means in theory, you now know your exact solution. The exact solution is whatever function has power series aix to the I, where the ai's start with these 3 terms and then obey this recursive relationship. So we can generate an approximate solution, if we want, to an arbitrary degree by generating a whole bunch of a sub i's. So with our power series solution and the recursive relationship and 3 initial terms given, we're going to generate an approximate solution just to continue discussing this one problem. We're going to generate a3, a4, a5, and a6. Okay, so let's just go through the first one by hand. A naught is 1, a1 is 2. So by setting I equals 0, we would get a sub 3. 1 over 0 factorial, that's 1, minus 0, 0, 0, so I can actually ignore this term. 0 minus 1 is negative 1, so this becomes plus a sub 0. So our numerator is 1, 0, plus a 0. We already know that a naught is 1, so the numerator is 1 plus 1, or 2. What about our denominator? Since I is 0, we just get 12. 2 over 12, in other words, 1 over 6. So similarly, using a1 and a2, you can generate a4. Then once you know a2 and a3, you can generate a5. And once you know a3 and a4, you can generate a6, and so forth and so forth, and we simply stop right here. So with our power series solution, we've determined a naught through a6, which means we can approximate our solution with a 6th degree polynomial using these coefficients. A naught is the constant term, 1, 2x, 1x squared, a 6th x cubed, 7/48 x to the 4th, 1/80 x to the 5th, 19 over 2,880 x to the 6th. This is now an approximate solution. Well, if this is our approximate solution, let's see exactly how it fits into our differential equation. Well, y prime would be given like this. It's just a polynomial, so computing a derivative is not terribly hard. Here's y double prime and y triple prime. So for our approximate solution, we now know y prime, y double prime, y triple prime, which means I could compute x squared plus 2 times y triple prime minus 3xy double prime, xy prime minus y. So we're going to take this polynomial, multiply it by x squared plus 2, subtract 3x times this one, add x times this one, subtract that one there. So with this approximated solution, once you throw it into the differential equation on the left and do all the simplification, here's what you'll end up with. And notice this is very close to the power series for e to the x. We wanted all of this to be e to the x, and the power series for e to the x begins 1 plus x squared over 2 plus x cubed over 6. The next term is x to the 4th over 24. And with our approximate solution, we got 7/16 x to the 4th. And so forth. So from now on, the terms are different, but it's rather remarkable to point out that we got many terms looking exactly the same, and the next one isn't that far off. So our power series, which solves this, we approximated with a 6th degree polynomial, and we saw that this 6th degree polynomial approximate solution really is an approximate solution. Thrown into the differential equation, we got at something that looks a lot like e to the x. All in all, what did we do? Power series techniques generalize very directly to higher order equations. But when working by hand, things get really unpleasant, okay? This was just a single example, and doing 3 examples of this length would have made this video interminably long. When working with a computer system, however, and especially if only interested in an approximate solution, this can be a quick and flexible way to find approximate solutions, and it is an extremely common computational technique to find approximate solutions when there's really no good way to find an exact one.